Hi, welcome to the Calculus 2 lecture series, and we are in the unit number 3, and we are working on some other applications of the integrations. So this is our lecture number 14, and for this lecture, we're going to take a look at how do we find the surface area when you rotating the functions here. Okay, all right, so now let's go ahead, go to our lecture notes, and let's get started. Okay, so this is our lecture number 14 here. Okay, so the key concepts here we're going to introduce is how to calculate the surface area, okay, of a solid revolution. Okay, so like so the surface area formula, so like in here I put pictures here. So if this is your function f of x, right? So if this is the function f of x, so if you rotating this f of x along the x-axis, you will generate this solid, right? You see this light blue solid is here. So what we try to do is here is we want to find the surface area of this light blue solid was generated by rotating the function y equal to f of x. So what I like to do here first is like, I like to write that down for the formula first. Okay, so then in here, the next things here, we're going to take a look at a brief proof of the, why we have this formula here. Okay, so let's take a look for this one. If I'm rotating around the x-axis, so the surface area formula will just be like a to the b. All right, so then you will have 2 pi and times f of x, and then times 1 plus f prime x, the whole thing square dx here. And these things here certainly looks very, very familiar, right? So from the, this is what we talk about is in the section previous lecture. That's the length of the arc, right? All right, so we're going to, so you will see why we have these ones here, because later we're going to do a very briefly proof, or you can rewrite these ones here. You will say this is AB, and 2 pi, because f of x, you can say it's y, and then you can have 1 plus dy dx to the square to the dx here, right? So this is a function y. So in here, so for this one, so we said a function y is equal to the f of x. So the same ways here, if the curve, right? So, if the curve, if you want to rewrite the curve as x equal to the gy here, then this surface area is fine. So the same ones here, for this one, we write the y equal to the f of x. Then you can say, hey, I want to rewrite this one to the x equal to the gx. Yeah, maybe I can do that, right? X to the gy, I'm sorry, is here. So x to the gy is here. Then the same surface area. So this surface area will be equal to, see here, it will be equal to from C to D. So right now, if you write the x to the gy, so what is the y's domain here? Then in here, you will have 2 pi, right? So it's 2 pi y. Then instead of is 1 plus dy, this is dy dx, right? So in here, you can say this is a dx dy to the squares here and the dy's here. And then both of them will give you the same, because it's the same solid, right? So they will give you the same surface area. It's just like, how do you write this function, the pink function we have over here, okay? So you can write y equal to the f of x and the x equal to, or you can write x is a function of y here. Okay, let's take a look at the proof of this one. It's pretty simple. All right, so the proofs here, it will show you here. So this is the solid. I kind of enlarge it a little bit. So in here, that's just like a similar, like a Riemann-Sum concept, right? So the similar like a Riemann-Sum concept, I just cut out a single strip. Okay, so this little pink things, this is my single strip here. So if you open it up, right? So if you open it up, if you cut out this simple strip, if you open it up, what you will get? You will get is rectangles, right? So you will get is a rectangle. And for this is the single, right? So this is the single strip we just cut out. It's just like what we show in the pictures here. So then what is here then? So from here, so this one here, when you cut out here, what is this one? This is the length. This is the segment length between the pi minus 1 and the pi's, right? So this will be this segments, the length of this arc, right? And then in here, then this side, the length, what is it? His one's here. So this will be the circumference. Correct? And then if you can cut it into many small and like a small strips, then you use the Riemann-Sum concept. When you add them together, what you're going to have is very close to the true surface area. Then you can let limit n approach to infinities, right? Then that's what the summation becomes the integrations here. All right, so in here, first thing here is how do I find the circumferences here? So the circumference. So if this strip is small enough, so then I know the radius here is some like, so it's like from here, right? So it's yi stars here, right? So this is the radius. So the circumference will be 2 pi what? Will be 2 pi yi star. Oh, you can say it's 2 pi f of xi stars, right? Okay, so this is my circumference. And so now in order to find the area of this strip, I need to have the length times width. The width is this arc length. And also, for the arc length here, so this is pi minus 1 pi. So this green one, remember from what? From what we did previously, this one's here, you can say this is 1 plus f prime xi star, then the whole thing square, and the delta x is here, right? So now, so the whole area is here. So we know the complete surface area will be what? So the complete surface area will just be, you add each little strip together. So it's 2 pi r. So r is f of xi star. And then times the length of the arc, the length of little arc is here. So this will be 1 plus f prime xi star to the square and what? Delta x, right? Then you will have I from 1 to n here. So I know by the Riemann-Sum concept, right? So by Riemann-Sum concept, then I know that in here, if the limit n approach to infinity, summation I from 1 to n, then this is 2 pi f of xi star, and this is 1 plus f prime f of xi star, the square delta x. So when you let the n approach to infinity, what will this one be? This will just be like what it become integrations, right? So it will be 2 pi f of x then times what 1 plus f prime x to the square dx, right? That's how do we get the formula. So the ideas, ideas how to, why the formula, the surface area formula is like what we, what we wrote here is pretty straightforward, right? So basically you just kind of doing the Renaissance concept, you cut it out strip here. Okay, all right. So now the next thing here is how do I do the rotations? The while ago the example we say is rotate about the axis, and now how about we rotate about the y-axis here? All right. So in here, if you take a look at the rotating about the x-axis, right? So this is your the circumference. This is your radius here. Let me highlight here, right? So this is your radius, right? So this is your radius. So it's y values here. So I know the surface area will be what? Will just be the 2 pi, right? So 2 pi what? The y, right? Y is my what? Y is my radius. So then remember the arc length functions, right? So then the remaining here, we will just say this is what? Is the ds here, correct? So the ds is the arc length functions here. So the same way, like if you take a look, if you are rotating along the y-axis here, so where is your radius? Here is your radius here, correct? So here's your radius. Then the surface areas here will be what? So the surface area here will just be, okay? So then this will be 2 pi. Okay, so 2 pi r, right now r is what? R is x. Then you still times the ds here, right? So here, because this is the radius, then you have arc length functions here, you times the ds. So the ds, you can use the ds like we talked about before. So the ds is depends, like you write the function as y equal to x or x equal to y. So the ds will be, you can use the dy dx square, right? Then the dx, or you can use the ds is equal to y plus dx dy to the square and the dy here. All right, so each one will work here. All right, so both of them, so like in here, if you do the dx here, then you do the dy dx, right? So in here, okay, so like in here, let me see here. Okay, so in here, if you do dy, then here is dx dy here. Okay, so the formula is pretty straightforward. Okay, so now let's take a look at some examples here. So the first examples, let's do a simple one. And so let's take a look here. So find the surface area of the solid revolution formed by the rotating area between x equal to 0 and x equal to 2, y equal to 0 and y equal to the x cubed over 3 along the x-axis here. So let's do a graph first. All right. So this will be, okay. So this is 1, 2, 3. And here, let me do this a little bit. So this is 2.4, 1.6, 0.8. And this will be -1, -0.8, -1.6, -2.4. So I'm my functions, because this is a cube function, 1/3 of the cube. So it will be something like this. All right. Okay, so this is between 0 and 2 is here. Okay, now I'm rotating along the x-axis, right? So you do like this. Okay, so you are rotating here, so you will have a what? You will have a solid like this, right? So now I'm going to find what I'm going to find the surface area of this solid, right? It's pretty cool. Okay, so now in here, so we'll set okay, so the y is equal to the x cubed over 3, so the dy dx is equal to x squared, right? So then I can just directly plug into my formula. So I will have a 2 pi y ds. So in here, I can just put it in the x's from 0 to 2, right? So this is a 2 pi. So this is my y's, right? So what is the y? Y is x cubed over 3. Then what is the dx? The ds is 1 plus dy dx squared. So it's x squared to the square, the dx here. And then this one's here, I can, well, simplify a little bit. So it's 2 pi 1/3. So this is 2 pi over 3. And I have here, this is x cubed. And then this is 1 plus x squared to the x squared dx. Then here I say, oh, I can do a u sub here, right? So I can do a u sub. So this one's here, I can integrate, it will be 1 plus x fourths. So du is equal to 4x cubed dx. All right. Then I can say the du over 4 is equal to the x cubed dx. Then you substitute here and do the integrations. So you will have, so this will be integrating, will be similar. So will be 2 pi over 3 times 1/4. I take that 1/4. Then this is the square roots of the u du. Then you plug in the top and the bottom. The limit is 1/17. So this one will become a pretty simple integrations. So this integration will be, okay, so the final answer for this one will be pi over 9 and 17 to the 3/2 minus 1 to the 3/2. So it's approximately equal to 24.118. Okay. All right. So let's take a look at the same problems here, right? So the same problem. Now let's take a look. How do we do if I'm rotating along the y-axis here? All right. So let me do the graph again. Okay, so this is a 1, 2, this is -1, -2. The scale I use is the same, 0.8, 2.4. And now I have, this is my functions, right? Oh, that's not a very smooth. So this is my functions, right? Okay, so now I'm doing is I'm rotating along the y-axis. So that means your function right now you're rotating along here. So here you will get a solid like this, right? So that means I'm looking for the surface area about this solid. And I'm going to rotating along the y-axis, right? Okay, so the same way for the y-axis here, let's try to say here. So we know the surface area will be, if I'm rotating along the y, will be 2 pi what? 2 pi x, right? So it will be 2 pi x ds. And then in here is x is from what? 0 to 2. Okay, so the ds, you can choose whatever you want. So that you have two choices. So this is a 2 pi x then you can choose the same things here, right? So it's 1 plus f prime x. We already did f prime x is x squared dx, right? So because we know f of x is equal to the x cubed over 3, we already did in the problem number 1. So this is x squared, right? Okay, so now you have 2 pi x and 1 plus you know, the x4s, and this is 0, 2, this is 2 pi x, and this is 1 plus x4 dx. So for these ones here, unfortunately, it's not an easy way to do the integration. So you can just plug this one into the, you know, the integration software, and you can get a value. So the value here is close to the 29. Okay, so it will be close to the 29.197 here. Okay, and so this is our first video. I'm, you know, in order not to be that video too long, I'm going to stop it here. So for our second video, then we're going to take a look at the remaining 2 problems. How do we solve it? All right. Okay. So guess I'll talk to you later. So, all right. Okay. Bye.